In this video, we're going to look at two more examples on absolute, conditional, or divergency. So the way that we work through these problems is, again, just by looking at them and determining whether or not we want to apply absolute convergence or if we want to apply conditional convergence. Now, again, remember, if we prove convergency, that means that it's not necessarily conditionally convergent. We might have to go up to one step further to prove that the absolute value convergency isn't satisfied. So for this one right here, I'm going to go ahead and start with the absolute value convergence, meaning that I'm going to look at this series right here, k equals 1 to infinity, of the absolute value of sine of k over k squared. Now, really what this means is that I'm looking at the summation of k equals 1 to infinity of sine of k inside an absolute value over side of k squared, because k squared is already positive. So the question is how can I prove that this series is either A, convergent, or B, divergent? Well, what's nice about this is I can actually come up with a comparison of how this thing compares to this thing. Because if you think about it, the absolute value of sine of k is always going to now be positive, and it's always bounded between 0 and 1. So in reality, this thing will always be less than or equal to 1. Which means that if I divide both sides by k squared, I have an actual comparison here. I know that this thing here is a p series with p equal to 2, which implies convergence. So this is real heavy, if you got to be very careful. We started with this series. We're trying to prove absolute or conditional convergency. I'm going to go ahead and try the absolute value first. That's going to give me this. I'm then going to get real smooth with my comparisons and say, hey, I know how the sine of k will compare to 1. Then I know that this compares to this in this format, and I know that this is really a p series that's convergent. So by a comparison test, the summation, let me do it this way. By a comparison test with the summation of 1 over k squared p series convergent, we know the series absolute value of sine of k over k squared will also be convergent. And again, we know this because this is a p series that's larger than this series. Since this series is larger than this series and this series is convergent, this one then also has to then converge. There's no way that this one can supersede that one then and get larger than it in any way. It can't diverge. It has to converge. So I know that this is convergent. Therefore, the original series, this is what we're talking about. We're not talking about the absolute value. We're talking about the original series, is absolutely convergent. And again, we're done, because if it's absolutely convergent, it can't be conditionally convergent, and it's definitely not divergent. So that's how to do that particular problem. It's a heck of a lot more dense, because you're kind of building in pieces that you have to know. You have to be willing to try, hey, I know sine of k will compare to 1 in some way. And we have to work with a comparison test. And again, I would argue that comparison tests are some of the more difficult problems to work through, because there's such unique cases that you kind of have to build into it. So let's look at one more example before we wrap this one up. And if we look at this particular example, we've got some form of an alternating series going on with k over k plus 1 is the a sub k. We can try the absolute value. I'm actually going to skip the absolute value case simply because let me go with the alternating series test. Now, again, the reason why I'm skipping the absolute value is because, well, the absolute value will imply some level of divergency. I don't think it's necessary to show it. And since we can go ahead and use the alternating series test to try and prove some things, we can start with a sub k is equal to k over k plus 1. I could work with that piece and first take the derivative and do all of that stuff again. I'm going to skip all that. I'm going to jump straight down to the second quality for the alternating series test. And the second quality for the alternating series test is as k goes to infinity of k over k plus 1. This thing is actually going to be equal to 1. So just by looking at the alternating series test, I'm looking at basically basic convergence, not conditional yet. I can't consider conditional because I haven't disproven absolute value convergence. But since the limit as k goes to infinity of k over k plus 1, which is the again, portion inside the alternating series of a sub k, I end up getting equal to 1. This fails the alternating series test, and if it fails the alternating series test, then by the alternating series test, with your limit, basically your div test, your divergence test, you can conclude that the series, the original series we have, k equals 1 to infinity, of negative 1 to the power of k, k over k plus 1, is divergent. And again, if I can conclude divergency, I'm done. If I conclude absolute convergency, I'm done. But if I can't conclude either one of those, and I can conclude that the original series on itself is convergent, then I have to then also prove absolute convergence still. It's the unfortunate situation that this particular section puts into place. But again, that's how you evaluate whether or not a series is absolutely convergent, conditionally convergent, or divergent.